Okay, in this video, we will talk about the other indeterminate forms, the product and the difference. Right? We know the 0 over 0 and infinity over infinity. Now let's continue. Okay, the first one for today, 0 times infinity. We know that this one function is approaching 0, one function is approaching infinity, and that product end up being indeterminate form, 0 times infinity. Please be 0 times something undefined, actually. And knowing that indeterminate forms, they are quite important and quite tricky sometimes. We have to be careful. Do not assume your answer right away. We have to investigate, like which function, theoretically, like which function is approaching faster. F is approaching 0 faster than G is approaching infinity, but this will be like which function is winning. If 0 is taking a lead, the answer will be 0. If infinity, the answer will be infinity, positive or negative, depends on the arithmetic. Or if they both, doing things at the same manner, the same speed, relative rates of growth, then will be the finite number. But the thing is, if we don't know, and of course we will not guess, we have to use the L'Hopital rule, but we are not allowed to use that rule directly to that form. We have to create this product, we have to rewrite this product as a quotient. That's what we will do. When we have 0 times infinity, for the product rule, we have two options. One option is we have to change for fraction. That means I can keep, for instance, 0 on the top and I can flip infinity, because dividing by the reciprocal means dividing by a number, maybe this way, dividing by a number means multiplying by the reciprocal. That means this is true. And now let's see what we have. We still have 0, and 1 over big number is a small number. That means we will rewrite this form in that form, and then we can apply the L'Hopital rule. Or depends on the function. You may decide to keep that infinity on the top, that function G. Then we will flip 0, and 1 over small number is a big number. And again, we managed to rewrite this product form in the quotient form, and these forms are good to apply the L'Hopital rule. And then it's a nice systematic procedure. We can get the correct answer applying correctly the L'Hopital rule. That's please remember, always flip to one function. Okay, then you can do it. Unless the one of the 0 infinity is already a fraction, then we can combine this together. Depends on the expressions. Okay, and I type this, we can see F times G, we can keep F of the top, flipped G, or we can keep G and flipped F. Then these fractions will lead to the good indeterminate forms, good for the L'Hopital. Okay, let's see. I even have the multiple choice options. X approaches 0 from the right-hand side, X times natural log of X. No relative rates of growth, please do not, because only at infinity works nicely. Right? Okay, that's what we have. X goes to 0, and natural log at 0 is negative infinity. That's we do have 0 times infinity. This is times. Yes, natural log of X. We all know how this function behaves. This is Y, this is X. Function looks like this, really slowly. This is 1. At 0, because domain function goes to negative infinity. That means we can see 0 times infinity. Okay, let's see what we can do. Actually, I will possibly leave natural logs and I will flip X. Let's see what we have. Natural log at 0 is negative infinity. 1 over small number is, and positive small number, it's positive big number. We are good. Let's try. If something is not working, you may always come back and flip it the other function. Okay. Okay, that means we will have a limit, and let's differentiate. X goes to 0 from the right-hand side. Derivative of ln of x is 1 over x. Derivative of 1 over x, negative 1 over x squared. When we simplify, what we have? 1 over x times negative x squared. Oh, too many. It's actually negative x. X goes to 0. We do not have negative 0. The answer is 0. Okay. Okay, but please make sure, do not say this answer right away. Yeah, do not say this answer. We definitely, for this type of limit, we have to have a strong reason. Okay, exercise number 11. Oh, limit at infinity. X times e to the negative x. X is infinity. E to the negative x at infinity is 0. That's we do have it. But let's see what we can do. This one we can easily rewrite, because we can rewrite without the negative exponent. That's when we're creating a fraction right away. Negative exponent goes to denominator with the positive, or the other way. Okay, now it's infinity over infinity, and I don't even have to apply the L'Hopital rule. E to the x grows faster, relative rates of growth. Denominator winning, the answer is 0. Oh, again 0. Okay, but you may apply the L'Hopital rule and check. Okay, limit as x approaches 3 from the right-hand side, and we have x minus 3, this goes to 0, times tangent. When x is 3 over 6, 2, 1, I mean 1/2, pi over 2. Tangent at pi over 2 is undefined. But let's see what tangent does. Function tan x looks like this. Yeah, maybe just the yx, this is pi over 2, negative pi over 2. And we will have from the right-hand side, that means this is the right-hand side, that's pi, that's 0. From the right-hand side, function goes down. That means it's negative infinity. Yeah? 0 times negative infinity is indeterminate form. We're not allowed to apply the L'Hopital rule right away. We need a fraction. In this case, not always this will work, depends on the other function. But when I flip tangent, 1 over tangent, I will have cotangent. I don't know if this is helpful, but I think it will nicely work. 3 minus 3 is 0. Cotangent at pi over 2, if x is 0, is actually 0. Yeah, because cotangent looks this. This is, I can maybe draw it at the same. Yeah, cotangent has, the green one is cotangent of x, 0 at pi over 2. Okay, let's apply the L'Hopital rule. That's we good to apply the L'Hopital rule. Maybe I can do it on the new line. Okay, derivative of x minus 3 is 1. Derivative of cotangent is negative cosecant square of the same angle. Follow the chain rule times derivative of that angle. Pi x over 6, derivative is pi over 6, and coefficient of x. Okay, let's substitute 3. That's we have 1. I can flip pi over 6, 6 over pi, and then negative, because we can see negative is not squared. That's maybe I can put on the top cosecant of pi over 2 squared. And what is cosecant? Cosecant is 1 over sine. 1 over sine. Sine at pi over 2 is 1. 1 squared is 1. So in the final answer, I can write this is just negative 6 over pi, because this will be 1. Okay. We can see finally we have a finite number. The answer is a finite number for this indeterminate form. Okay, and now we can have more and more examples. You can practice on your written homework, you can practice on your online homework. But yes, that's the way to deal with 0 times infinity. Okay, another one for this session is infinity minus infinity. Both of the function goes to infinity, and we end up having a difference. And the same constant battle. Yes, the same contest. If the first infinity is winning, it's infinity. If the second infinity is winning, it's negative infinity. If both of them are like compromised, yeah, then will be finite number. The thing is, again, we have to, in order to apply the L'Hopital rule, we have to change the difference to quotient. That's what we can do. We may have a couple of algebra things. If both of the infinities, the functions, are fractions, for instance, we can use common denominator and rewrite as a one fraction. Or we may notice, for instance, that we do have a common factor. We can factor out, we will have product, and from the product, we know how quickly we can get the quotient. Or rationalize denominator or numerator also will create a fraction. Depends on the function, depends on the expression. You will use definitely appropriate algebra steps. Okay. Secant of x minus tangent of x. Secant is 1 over cosine. That's me. Let's actually check 1 over cosine. And what is happening at pi over 2? Cosine at pi over 2 is 0. And from the left-hand side is actually, oh, wait a minute, it's positive infinity. It's actually positive. That means it's positive. 1 over small number is positive, it's big number. I'm sorry, I was just thinking this is cosine, this is pi over 2, and it's 0, but on the left-hand side is above. That means it's positive. 1 over small number is a big number. Now, tangent. Tangent at pi over 2, from the left-hand side, we remember it was infinity. Let's come back to tangent. We can see tangent, and that's the left-hand side. Left-hand side function goes to positive infinity. But we can also think about the fraction which we will use. Tangent is sine of x over cosine of x. Sine at pi over 2 is 1, and cosine is 0 from the right-hand side. That means it will be infinity, but it was a difference. Okay, we have infinity minus infinity. Let me remove the plus because it's confusing. Okay, but we can see my first step, checking if this is indeterminate form. We did create a fractions, cosine of x and sine of x over cosine of x. Pi over 2 from the left-hand side. That means now we can, because we remember we have to rewrite in terms of, we have to rewrite difference in terms of the quotient. We are lucky, the same denominator, then we will have just 1 minus sine of x. Sine of x at pi over 2 is 1, 1 minus 1 is 0, cosine at pi over 2 is 0. We are allowed to apply H, the L'Hopital rule. Pi over 2 from the left-hand side. Derivative of negative sine of x is negative cosine, 1 is 0. Derivative of cosine is negative sine of x. Okay, and what we getting? Cosine at pi over 2, negative and negative will be cancelled out. And sine at pi over 2. This means cosine at pi over 2 is 0. Sine at pi over 2 is 1. However, that's okay. 0 over 1 is 0. Okay. This actually, it's infinity minus infinity because that's the original. We've got 0. It's okay. They are, yeah, we may have a 0. Okay, let's see. This one, I can leave it for you because it's the same idea. Okay, do it this one. And this one, I have this one. Let me check. I have the, we can do this one. Okay, you can try, okay, because it's nice common factor. It's definitely infinity minus infinity. E to the e at infinity is infinity, e to the x at infinity. That's when you can maybe factor out. You can check this one because I don't want to keep you too long. We can maybe do this one and this one. Okay, 2 of them and we will be done. Okay, 1 natural log at 1 is natural log at 1 is 0. From the right-hand side, it will be positive. That means 1 over small number is a big number. Okay, this is infinity. And then 1 minus 1 is 0. This is a little bit more. That means, yes, we do have infinity minus infinity. Since we have two fractions, let's get a common denominator. Common denominator is natural log of x times x minus 1, just the product of these two. That means this x will be multiplied by this, and that negative 1 will be multiplied by natural log. Let's simplify a little bit. We will have x squared minus x minus natural log. And this one, let's maybe keep the product. Okay, 1 minus 1, natural log at 1, 0. Natural log at 1 is 0, 1, it's actually 0. Okay, we allowed to use the L'Hopital rule. Let's check. Derivative of x squared is 2x minus 1. Derivative of natural log of x is 1 over x. Now, actually, in the denominator, we have to use product rule. Derivative of natural log of x is 1 over x times x minus 1 plus natural log of x times derivative of x minus 1 is 1. Okay, let's see what we have. We have 2 minus 1 minus 1. Oh, well, 0. This is 0 because 1 times 0 and natural log at 1 is 0. We have to use it again. But before I use it again, I can maybe just to this, I will keep 2x minus 1 minus this, and I will distribute 1 over x times x is 1. 1 over x times negative 1 is negative 1 over x, and natural log of x. Okay, then we do not have any, it's still 0 over 0. Any product rule in the denominator. Okay, hope it will be done, because I don't have enough room for the third time. Derivative of 2x is 2, derivative of negative 1 is 0, derivative of 1 over x is negative, then I will change for positive, 1 over x squared, negative 1 over x squared. Okay, now derivative is 0, the derivative of negative x, negative 1 over x is negative, that means negative and negative will become positive, negative 1 over x squared. Yeah. And derivative of natural log of x is 1 over x. Okay, 1. Oh, 1 over 1 is 1. 2 plus 1 is 3. And 1 over 1, 1 over 1, 1, 1 plus 1 is 2. 3 halves. Finally, we have that's it's interesting. Eh? Infinity minus infinity gave us a finite number. So we can see, could be anything, could be infinity, could be 0, could be a finite number. We did, 3 examples. And I did skip 2, but you may work on them. You may definitely work. And let's finalize this session with that difference. And that maybe we can avoid the L'Hopital rule. Natural log at, let's actually check. Natural log at 1. That means 1 minus 1, 0. That means this is natural log at 0 from the right-hand side is negative infinity. We know that natural log goes down. This is logarithmic function, ln of x. And at 0 from the right-hand side goes down. And then we have minus. And again, this is also natural log at 0. Then natural log at 0 is negative infinity also. As we have negative infinity plus infinity. That means this is still a difference. Yes, we can see it's still a difference. Okay, I thought that it's different, but let's do it. Let's actually see. We can definitely use the property of subtracting the same logarithm, the same base. We may divide. Yes, we may divide the inputs. And now, since this is a continuous function, we can only logarithmic function will stay outside, and the limit we have to compute for the inner function. x over 7, x, I mean x to the power of 7 minus 1, x to the power of 5 minus 1, and x goes to 1. Okay, I really thought that this is limit at infinity, then it will be easy to figure out, but no, I think we have definitely 0 over 0 inside. We will apply the L'Hopital rule. Okay, that means we will apply the L'Hopital rule. We may factor out, but I don't know if this will be easy for this power 7 or 5. If the L'Hopital rule occurs, this will be 7x to the power of 6 derivative, 5x to the power of 4, and once is 0. Now we can simplify. Oh, actually, we can simplify definitely, but if x is, we can simplify a little bit. This will be just 7 over 5x squared. X is 1. Okay, that means the final answer, because this limit is just x is 1. That means x squared is 1. 7/5 is the inner function, and outer value stays, outer function, natural log. Natural log of 7 over 5. But it wasn't so obvious. Okay, it wasn't so obvious. Yeah, but it's finite number. Difference of two infinities, it's a finite number. Okay, as promised, this is the last example. Enjoy. And then we still have what we have. We have this, power forms. Please check my last video for the indeterminate forms about the power forms. Thank you for, let's keep this one. Thank you for the second session of the indeterminate forms. And you have one more. Enjoy. Thank you.